This video was sponsored by Brilliant. What happens when we give a CPU an instruction it doesn't know? Does the program crash? Does the operating system show an error? Or does the whole computer just go? A couple of episodes back, we were talking about instruction set architectures, a set of rules that different CPU models can follow. So even though they may be completely different internally, they can still remain compatible with each other. So during the compilation process, we usually target a specific ISA. That way, the same executable file can be compatible with old, current, and even future processors that implement that ISA. Or at least, that's the idea on paper. In reality, instruction set architectures are kind of a lie. Before continuing, I just want to mention that since more and more people have been asking me for a low-level programming course, I've been giving the idea a lot more thought lately, but more on that at the end of the video. From a programmer's perspective, we can think of an instruction set architecture as the set of instructions that a processor can understand and execute. When a new instruction set architecture is released, it comes with a large initial set of instructions. But as time passes and chip designs improve, manufacturers find better ways to perform certain tasks in silicon, so they introduce new instructions that weren't part of the original ISA. Now, if you think about it, once you add new instructions, you could argue that this should be considered a different instruction set architecture. Imagine we have ISA1 and then extend it with some new instructions to create ISA2. A program compiled using only ISA1 instructions can still run on a processor that supports ISA2 because all the instructions from ISA1 are still available. But a program compiled using ISA2 instructions can't necessarily run on a processor that only supports ISA1, simply because that processor doesn't recognize some of those newer instructions. So from a strict compatibility perspective, these should be treated as distinct instruction set architectures. But doing that every time a few new instructions are introduced would completely fragment the architecture and make software compatibility much more complicated. So instead, manufacturers usually define the original set of instructions as the base ISA, while additional sets of instructions introduced later are called ISA extensions. For example, x86-64 has accumulated extensions such as SSE, AVX, AVX2, and AVX512 over the years. But instead of saying that newer processors are incompatible with older ones, manufacturers simply say that the newer processors support additional features. Okay, but this marketing strategy doesn't solve the main problem. What happens if we compile a program using one of those ISA extensions and then try to run it on an older CPU that doesn't support it? Does the CPU just skip the instruction? Does it interpret those bits as some other instruction? Does the entire computer crash? And more importantly, how can a processor recognize that an instruction is unsupported in the first place? Good questions like those are better with intuitive explanations. One of the biggest problems with learning in this AI era is that models can give you the answer before you have had the chance to actually understand the problem. That might help you finish an assignment, but it does not necessarily help you become better at solving similar problems on your own. On top of hundreds of interactive courses, Brilliant takes a different approach with Koji, its interactive AI tutor for students, including those at the college level. Instead of simply revealing the answer, Koji asks questions, breaks the problem into smaller steps, and guides you toward figuring it out yourself. He can even draw directly on the screen to help explain what is happening. That is the kind of tool I wish I had when I was learning some of these concepts for the first time, especially in those moments when I understood most of the topic but could not figure out exactly where I was going wrong. If you want to learn new concepts by challenging yourself while still receiving helpful guidance, Brilliant may be perfect for you. You can try Brilliant's tutor for free by accessing brilliant.org/coredumped or clicking the link in the description or scanning the QR code on the screen. Brilliant is also offering CoreDumped viewers 20% off an annual subscription. And now, back to the video. Marketing or not, CPU manufacturers still need a way to deal with these compatibility problems whenever they introduce a new ISA extension. Believe it or not, if we try to run a program compiled for a newer processor on an older one, the operating system will normally load it and the CPU will start executing it just fine. Problems emerge only when the processor reaches an instruction it doesn't support. And notice what I just said. only when the unknown instruction is reached. Here's the key to avoid the problem: turning that when into an if. What I mean is that we can place ISA extension-specific code behind conditional branches, making sure that a processor never even attempts to execute instructions it doesn't support. But that raises another question. How can a program determine which instructions the CPU it's currently running on actually supports? Well, the base ISA usually provide an instruction specifically for retrieving information about the processor. On x86-64, it's called CPU ID. At the most basic level, CPU ID can give us information identifying the processor. So theoretically, we could identify the CPU model and then look somewhere else, a specification file on disk, or maybe even the internet, to find out which ISA extensions that processor supports. But that would be a terrible solution. A local database might not exist or might be outdated, an internet connection might not be available, and accessing either one would be unnecessarily expensive. So CPU ID does something much more useful. It allows the processor to report its capabilities directly. Here's how it works. Before executing CPU ID, we place a number into the EAX register, and for queries that require it, another number into ECX. These numbers are known as a leaf and a subleaf, which are really just low-level query numbers. They tell the processor, I want this specific information about you. You can think of CPU ID almost like a function. Depending on those parameters, the processor returns different information about itself. That's how software can discover things like the CPU vendor, processor family and model, cache information, topology, how many cores are available, virtualization capabilities, supported instruction set extensions, and a whole lot more. For this video, we're interested in ISA extensions, and two particularly important queries are leaf1 and leaf7. For example, if we want information about newer extensions such as AVX2 and AVX512, we can put the number 7 into EAX, the number 0 into ECX, and then execute CPU ID. The CPU returns four 32-bit values in EAX, EBX, ECX, and EDX for a total of 128 bits of returned information. For these feature identification queries, many of those bits act as individual capability flags. A 1 means that the corresponding feature is supported. A 0 means that it isn't. Here, for example, the values the CPU returned in the EBX register can tell us if a CPU supports the AVX2 and AVX512 ISA extensions. If different processor models have different capabilities, they will return different values when running this exact same sequence of instructions. Instead of maintaining some enormous external database, mapping every CPU model to every instruction it supports, the processor can directly tell software, this is who I am and this is what I can do. All in a few instructions, meaning the information is available in a matter of nanoseconds. So, with a little bit of inline assembly, we can read those bits and implement the functions to check if certain extension is available, and then simply use those functions in our conditional statement. At the silicon level, the older CPU hasn't somehow become compatible with AVX512. It still has absolutely no idea how to execute those instructions. We're simply arranging the program so that it checks the processor's capabilities before choosing an execution path. A newer processor might follow this path, while an older one follows this one, and an even older processor might fall all the way back to this. The unsupported instructions can still be sitting right there inside the executable. The older processor remains completely incapable of executing them. The trick is simply making sure it never reaches those instructions. Okay, but that still leaves the original question unanswered. What actually happens if we let the older CPU reach an unsupported instruction? Well, let's find out. This old laptop does not support AVX512, so let's see what happens if we try to run the AVX512-based simulation program I showed in my previous video on it. Okay guys, here we go. 3, 2, 1. Okay, it is obvious that something went wrong. But wait a minute. Those of you who have been around this channel for a while probably know exactly where this is going.
Oh my God! Okay, it's happening!
You see, for the CPU, it's actually very easy to identify an unknown instruction. When the decoder receives an encoding that the processor doesn't support, instead of freaking out or trying to execute something random, it raises an exception in form of an interrupt. And because this happened while our program was running, the exception transfers control to the operating system. And now it becomes the operating system's problem. On Linux, the kernel translates this exception into a signal sent to our process, the illegal instruction signal. And unless our program has explicitly installed a handler for that signal, Linux applies the default action, terminate the process and dump the core, which explains exactly what we just saw. And if that sounds familiar, that's because something very similar happens with segmentation faults. When a process tries to access invalid memory, the CPU's memory management unit detects an exceptional condition, the operating system gets involved, and Linux sends the process a signal. In the case of an invalid memory access, that's usually SIG-SEG-V. I have a whole video talking about this on the channel, so you might want to check it out. But here's where things get even more interesting. The default behavior is to terminate the program, but it's only the default. There are only two signals we cannot install a handler for, and SIG-IL is not one of them. Which means that instead of immediately terminating when an unsupported instruction is executed, we could technically catch the signal and do something about it. Maybe report to the user that the CPU is unsupported. Maybe switch to another implementation that only uses older instructions, such as we did with the conditional statements before. Or obviously, the most reasonable solution.
No! God! No! God, please, no! 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 No!
I've been planning a more in-depth and structured course for people who want to get into low-level engineering, and I'd really like to know what topics you'd want me to cover. If there's something specific you've struggled with or always wanted explained properly, let me know in the comments below. And let's wrap things up for now. If you'd like to support the channel, don't forget to check the sponsors in the description below. Or consider subscribing. And if you liked this video or learned something new, please hit the like button. It's free, and that would help me a lot. See you in the next one.